Okay, Assalamualaikum and a very good morning. Okay, next we are going to discuss on the microstrip or patch antenna design. So there are variety of microstrip patch antenna shapes as shown: square, rectangular, dipole, circular, and etc. But there are two the most common shapes, which are the rectangular and circular patches. Okay, this is the basic configuration of microstrip antennas. It's made of patches. Okay, for example, rectangular patches, and it's backed by a ground plane. And both the patch and the ground plane is usually made of high conductivity metal, typically copper, and it has a very thin thickness, and it's fed by a microstrip transmission line. And the patch and the ground plane is separated by a substrate material, dielectric substrate, for example, FR4, Rogers, wearable materials, and etc. And the substrate has a thickness of H and the relative permittivity epsilon R. Okay, so the microstrip patch is designed so its pattern is maximum normal to the patch on broadside radiator, so it's maximum radiation on top of in that direction above the radiating structure. Okay, the patch antenna usually is a narrow band or wide beam antenna. And the simplest patch uses have 1/2 wavelength long, so the typical length is lambda over 2. So it acts as the half wavelength dipole antennas. And in fabrication, as mentioned earlier, is usually mounted the shape of the metal, the patch, it's mounted on the dielectric substrate, and it backed by a continuous metal bonded to the opposite side of the substrate, which forms a ground plane. Okay, these are the advantages and disadvantages of microstrip patch antennas. The advantages are low profile, conformal to the surface, so it can easily be mounted on bent or curvature surface, and then low cost, mechanically robust, compatible with monolithic microwave integrated circuit design, and it's versatile in terms of the resonant frequency, polarization, radiation patterns, and impedance. And some of the disadvantages of microstrip patch antennas are low power, narrow bandwidth, large EM structure outside operating bands. Okay, usually microstrip patch antenna works within UHF up to 100 GHz frequency band, and in large arrays, the trade-off between the bandwidth and scan volume, and it does possibility of large physical size at VHF and UHF frequency bands. Okay, these are typical applications of microstrip antennas, such as in aircraft and ship antenna system, missile, satellite communication, and mobile radio communication, also in remote sensing, biomedical, and others. So some applications for each of the mentioned system are as shown. Okay, so how the microstrip patch antenna radiates. Okay, so the radiation mechanism in patch antenna is due to fringing effects or fringing fields, which appears at the edge of the patch structure. Alright, so the patch antenna can be viewed as an open circuit transmission line. Let's say the maximum voltage appears at one end of the patch structure, while at half wavelength away from the maximum voltage position, the voltage is minimum, so negative V here. So the fields underneath the patch is as shown in this figure. So where the fringing fields appears around the edge of the structure. Right, the fringing effect makes the patch antenna size wider after excitation, in which the fringing effect has caused the effective electrical length of the patch appears longer than its actual physical length, L. So the L effective is the value that considered in the resonance frequency calculation, not the actual physical length L. Right, the fringing E fields. Okay, so there's fringing at the edge of the structure. So the fringing fields at the edge of the microstrip antenna add up in phase and produce the radiation of the microstrip antenna. So besides the E field at the edge of the structure, there's also currents add up in phase on the patch and also on the ground plane. But the current on the patch is in opposite direction to the current in ground plane. So therefore, the current is cancelled out. So that is why the patch antenna is also known as a voltage radiator if compared to the wire antennas that known as current radiator. So the larger the fringing fields, the better, because better radiation can be produced. So in which the fringing fields also helps in giving more directive radiation pattern. However, the resonant frequency may be shifted due to the fringing effect if compared to desired frequency. And the fringing fields can be added up or can be enhanced further by increasing the width of the patch structure, increasing the thickness of the substrate, and also reducing the dielectric property or dielectric constant of the substrate materials. Okay, next, let's have a look on the feeding techniques in microstrip patch antenna design. So this is one of the important parameters in design process, in which the feeding techniques influence the input impedance and characteristic of the antenna. So there are four common types of feeding techniques, which are the microstrip feed line, coaxial feed line, aperture couple, and proximity couple feed. Right, so it can be classified into two. The first one is the direct excitation. So for example, the microstrip feed line and also coaxial feed line. Or the other one is the indirect excitation. Okay, in which using electromagnetic coupling or aperture coupling and a coplanar waveguide or proximity couple feed technique. So in which in indirect excitation, there's no direct metallic contact between the feed line and the patch. Okay, the next few slides summarizes different feeding techniques, the configuration, advantages and disadvantages of each technique. So the first one is the microstrip line technique, in which it is a conducting strip, in which the width is much smaller compared to the to the width of the patch. So this is the width of the patch. All right, so this is the microstrip line feeding microstrip. and the width is much smaller compared to the width of the patch. And the advantage of this technique is easy to fabricate, and it's simple to match between the feeding line and also the patch structure by controlling the insert position. So the insert position can be varied from the edge of the patch structure, and it can be etched on the same substrate, right? But the drawbacks of microstrip line feeding technique, so when the substrate thickness increases, so the surface wave and spurious feed radiation increase, and the bandwidth also quite narrow, between 2 to 5% only, and at higher frequency range, millimeter wave range, the size of the feed line may be comparable to the patch size, so it will increase undesired radiation. Okay, next is the coaxial feed or prop feed feeding technique. So there's a coaxial cable connected to the patch structure. So the inner conductor of the coaxial cable is attached to the patch here, while the outer conductor is connected to the ground plane. So the coaxial feeding technique is easy to fabricate, have low spurious radiation, and simple matching by controlling the feed position, but it has narrow bandwidth, between 1 to 3% only, and it will be a bit difficult to model or to fabricate when the structure has a thicker substrate. And another consideration in designing a microstrip antenna by using coaxial feed is the coaxial feed introduces an inductance into the feed. So therefore, this needs to be taken into consideration as the height increases. All right, and the probe may also radiate, so it will lead to undesired radiation in undesirable direction. So proper length and also proper position of the probe need to be considered in designing microstrip antenna by using coaxial feed probe feed technique. The third one is the aperture feed technique, in which the feed circuitry, okay, the transmission line for the feeding, is shielded from the antenna on top by a conducting plane with a hole or aperture to transmit the energy to the antenna. So usually high dielectric constant material is used for the bottom substrate if compared to the upper substrate, which uses lower and thick dielectric constant on top substrate. And the ground plane in the middle that isolate the transmission line or the feeding from the radiating element isolates the feed from the radiating element, and it minimizes interference of spurious radiation. And this is better to control the pattern and also polarization of the antenna. And the substrate electrical parameters, the property of the substrate, the feed line width, and slot size and position can be used to optimize the design. So the slot size, the width and length of the slot size, the substrate dielectric constant, and the feed line width can be used to control the characteristic or the property of the antenna radiation. And the matching is performed by controlling the width of the feed line and the length of the slot. However, the aperture feed technique is difficult to fabricate, and it produces only very low bandwidth, between 1 to 4% only. Okay, the first one is the proximity couple fit technique, also known as electromagnetic coupling. So in which the feed line is placed between the patch and the ground plane, separated by two substrates. So you have your patch on top and you have your ground plane at the bottom. Okay, so separated by two layers of substrate. Okay, so substrate 1 and substrate 2. So this is your patch and this is your ground plane. Alright, so the proximity couple fit is introduced here, somewhere in between the two substrates. Oops. Okay, so the length of the feeding stub and the width to line ratio of the patch can be used to control the matching. Okay, the advantage of this technique, it includes the elimination of spurious feed network radiation, and it can increase the bandwidth due to the increase in the overall substrate thickness. So now it at least double the thickness of the substrate, and it has larger bandwidth, as high as 13% if compared to other methods which only produce below than 5% bandwidth. And it is also easy to model and has low spurious radiation. However, the drawbacks of this technique, it has two layers need to be aligned properly, and it increases the thickness of the overall structure, and this may also cause a difficult fabrication process. Okay, let's have a look on the steps or procedure to design a microstrip patch antenna. So the first step is to specify the parameters or the characteristic of the patch, if relative permittivity or direct constant, the resonant frequency required, and the ratio between the H, the thickness of the substrate, divided by the lambda naught is the free space wavelength. Next, we need to determine the width of the patch. So you have the L and also the width of the patch. Okay, so determine the width. So the width is given by this equation, W equal to V naught. It is velocity of the speed of light, and then divided by 2FR. FR is the resonant frequency required, and multiplied by the square root of 2 divided by epsilon R plus 1. Epsilon R is the relative permittivity of the substrate. So for an efficient radiator, a practical width which leads to good radiation efficiencies can be simplified or can be determined by using this equation. And once you have the W, you need to determine the effective dielectric constant. So I'll show you what is effective dielectric constant if compared to epsilon R. So epsilon EF, F is the effective dielectric constant, which given by this equation. So it depends on the epsilon R, the relative permittivity of the substrate material, and the ratio between the H, the thickness, and also the width of the structure. And this is valid for the ratio W divided by H is larger than 1. Alright, next we need to determine the delta L. So what is delta L? As we have seen earlier, that due to the fringing effect, the length of the antenna structure appears longer than its actual length. So the electrical length appears longer than its actual length. Therefore, the difference between the the electrical length to its actual length is given by delta L, in both sides. All right, so this is your antenna, the actual L. So due to the fringing effect, the antenna appears longer, so the electrical length appears longer in both sides. All right, so part on the one edge determined by delta L, and on the other edge separated by about lambda over 2 length of the antenna, another delta L. And once we have the delta L, we can determine the effective length. So this is the electrical length due to the fringing effect. And lastly, we can determine the actual length of the antenna structure or of the patch. Okay, so once you have the effective dielectric constant, that epsilon ref, so you can determine the delta L by using this equation. So you need to use the effective dielectric constant values into this equation, so you can determine the delta L. Once you have the delta L, you can have the actual length of the patch antenna. Okay, so what is the effective dielectric constant? Epsilon ref. So as seen earlier, due to the fringing effect, we can see that there's lines at the edge of the patch structure towards the ground plane. So these lines, you can see that it is basically non-homogeneous lines, which the lines basically lies within two different substrate materials or dielectric materials. So here we have the air, and here you have the substrate. Okay, so due to this different property of the air and the substrate, therefore we need to consider the effective dielectric constant considering both. Okay, the lines lies within two different substrate material, the air and the substrate. Okay, so the effective dielectric constant can be approximated by using this equation. And for the effective length, I have mentioned earlier, due to the fringing effect, so the antenna, the electrical length of the patch antenna becomes longer if compared to its actual length or actual physical length. Therefore, the difference is defined by delta L, in both sides, on the one edge of the structure and at the other edge of the patch structure. And from the delta L, so we can determine the effective length. So the effective length will be used in the resonant calculation, and we can also determine the actual length of the patch structure. And again, V0 is the velocity or the speed of light, Fr is the resonant frequency required, and epsilon ref is the effective dielectric constant. Okay, let's have a look on example. Design a rectangular patch resonating at 10 GHz using a substrate of RT duroid 5880. The dielectric constant of the substrate is 2.2 and the thickness is 0.1588 cm. Alright, so in order to solve this, you need to remember the steps. So the first one is to determine the W, the width of the patch. So you have the patch structure, and then you have the substrate. Okay, so the substrate material given the dielectric is 2.2 and its thickness H equal to 0.1588. Right. The first step is to determine the W. So from the equation given, so W equal to V0, the speed of light or velocity, the free space velocity of light, to Fr, and 2 divided by epsilon r plus 1. So as mentioned earlier, I would prefer you to write down the general equation before you put in any values into the equation and consequently solve the problems. Right, so V naught 3 times 10 to the power of 8 to the resonant frequency is 10 gig, and square root of 2 divided by the epsilon r equal to 2.2 plus 1. So you should get the width W equal to 1.186 cm. Alright, so you take note with the unit. If you use meter, then make sure it is in meter, or else use the conversion. So the second step is you need to get the effective dielectric constant. Alright, so from the previous calculation, the first step, you get the W equal to 1.186 cm. So the second step is to determine the effective dielectric constant. So given by this equation, so epsilon ref equal to epsilon r equal to 2.2 plus 1 divided by 2 plus epsilon r minus 1 divided by 2 multiplied by 1 plus 12h divided by W. Right, so don't forget to the power of minus half. Right, so epsilon r as given is 2.2 plus 1 divided by 2 plus epsilon r 2.2 minus 1 divided by 2 multiplied by 1 plus 12. The h given is 0.1588 cm divided by the width also in cm, 1.186 to the power of minus half. Right, so the effective dielectric constant, you should get 1.972. Okay, next you need to get the delta L, the extension of length due to the fringing effect. Okay, so the delta L can be determined by using this equation. So delta L over h equal to 0.412 multiplied by epsilon ref. Okay, make sure you use the correct value, 0.3 multiplied by the W over h plus 0.264 divided by epsilon ref minus 0.258 multiplied by W over h plus 0.8. Okay, so delta L, the value that you are about to find or to calculate, so you can multiply 0.412 multiplied by h, 0.1588 multiplied by the other parameters. So epsilon ref from the earlier calculation equal to 1.972. So 1.972 plus 0.3 multiplied by W. So from earlier calculation, W equal to 1.186, also in cm. So 1.186 divided by your h given is 0.1588 plus 0.264 divided by 1.7972 minus 0.258 multiplied by W, 1.186 in cm, H in cm as well, 1588 plus 0.8. Okay, so multiply them. You should get delta L equal to 0.081 cm. Okay, so once you have the delta L, you can determine the LF, L effective, okay, by using this equation. So L effective equal to L plus 2 delta L. So since you don't know the L, so you can calculate the L effective by using this equation. So V naught divided by 2FR ref. So 3 times 10 to the power of 8, 2 and 10 gig, and epsilon ref 1.972. So L effective equal to 1.068 cm. Okay, so once you have the L effective, then you can get the actual length, right? So from here, the actual length so the L equal to L effective minus 2 delta L. L effective minus 2 delta L. So L effective is 1.068 minus 2 times of delta L, 0.081 cm. So the actual length is 0.906 cm. So this is the length of your antenna, and you can use the CST simulation to verify this. Okay, whether if you insert the length and the thickness and the property of the substrate and try to simulate whether you can get the antenna resonant at 10 GHz sonars. Okay, we have done the first part of microstrip patch antenna design, so we will continue with the second part later on. Thank you.